All right, let's go ahead and get started. Get the sign-in sheet passed around. No real big announcements today. I went ahead and decided office hours. I'm going to go with Monday, Tuesday, Wednesday, Thursday, 1 to 3. But I mean, I'm pretty easy to get a hold of, so it's not that big of a deal either way. One other thing I thought I would mention, I don't have it on the announcement slide. I'll try and be confidential with it because I mean it's your all's educational records and whatnot. But long and short of it is, I figure since I've got some time, I want to try and get an early start on this. We sort of need to go through and make sure that everybody is qualified and able to enter senior design next year. So I'm going through and sort of slowly working on an analysis to make sure that everybody's got all the classes and whatnot. Because senior design is one of those classes that we put you in. So I want to make sure that I've got everybody that I'm supposed to have on the list. Okay. Reason I'm saying this is because what would help me right now is like after class, once I get the sign-in sheet, if any of you all are still on the old curriculum, let me know. Okay. Because I need to know that. So if some of you, it's no big deal if you are, just let me know. Tell me that after class. But I'm sort of going through and making sure that everybody's on the list. Yes?
Don't do it.
All right, let me say that if you're, when in doubt, go ahead and just assume you're on the new curriculum, okay? But if it becomes an issue, we can talk about it. Let me say this. For most students, it's not going to matter whether or not you're on the new curriculum or the old curriculum because the requirements to get into senior design didn't really change a whole lot. So it shouldn't matter either way. Bless you. Bless you. All right. Like, for instance, based on what you had last semester and based on what you're having now, I can pretty much tell you're probably going to qualify either way, so it's not a big deal. But I'm just going through and doing my diligence, and I kind of need to do this, or somebody needs to do this, because senior design is one of those classes that you sort of have to be manually entered in. So I want to make sure that I've got everybody. I don't want anybody to fall through the cracks is what I'm getting at. So if you're on the old curriculum, just tell me after class, and we can make sure, because there's nowhere in BERT that is listed. So everybody good? Everybody good? All right. So I want to get into tributary. Bless you. I want to get into tributary area today because by and large your homework assignment, your homework 1, is going to discuss is going to be in reviewing tributary area and gravity loads. So we kind of talked about this last time. We didn't really get into any major examples. Let me just sort of briefly recap what we talked about last time. So I mean, we introduced the course and whatnot, but one of the big ideas that we got across last time was this idea of uncertainty in engineering and just the idea of a design philosophy. Instead of just blanketly applying a factor of safety, what we do in structural engineering is we apply different load and resistance factors depending upon what we're talking about. So different factors for dead loads than there are for live loads and et cetera. So what I want to talk about today is really get into the load side of things and look at tributary area and how you actually perform a load takedown. In other words, given a structure, a typical representative real-world structure and given some representative real-world loads, how do you take that real-life scenario and turn it into a simply supported beam with a uniformly distributed load, something that we all can analyze and ultimately design. That's kind of the point of what we're talking about today. And in order to do that, in order to perform that, you need to understand the concept of tributary area, which is how much of a given, let's say, floor system a particular member is responsible for. And we talked about last time how that is typically defined as halfway over. So if you have a bunch of floor beams, let's say, supporting a given floor area, one floor beam is going to be responsible for all of the floor area halfway over to the next one and halfway over to the next one. So that's how we're going to generally define tributary area. So what we're going to do here in a little bit is we're going to take a representative floor system very similar to this one, and we're going to take a floor load up, I believe it's like 20 to 25 pounds per square foot. And we're going to take that load and start developing analytical models that we could analyze and then design. So just so everybody remembers, you sort of got to think of this as if it's sort of a hip bone connected to the leg bone type of analysis. Think if I'm standing on this floor, you know, where does the load go? Well, it goes from the slab to the beam, then from the beam to the girder, from the girder to the column, from the column down to the ground. Does that concept kind of make sense? Are you okay with that? Okay, so here's the floor system that we're going to look at. So just so everybody remembers, the black squares that you see on the diagram, these are columns. Okay, so again, we're sort of sitting. Imagine we're sitting in a helicopter. We're looking down. We're seeing the columns sticking out of the ground, and we see a series of floor beams going vertically and a series of girders going horizontally. So for the example, okay, so we have a load of 20 pounds per square foot. What we're going to do is we're going to do tributary area sketches for the following elements. So we're going to look at a typical interior beam. We're going to look at a given girder and a given column, but we can extend this and sort of look at everything. And then we're also going to determine what would be the load on a typical interior beam, what would be the loads on a given girder, and what would be the loads on a given column. Does that sound good? Are you okay with that? Okay. So let's start off with a typical interior beam. So let's say we're looking at, let's see, so we got C2, D2, C2, D2. Let's say we're looking at this beam right here, okay? So just so everybody's familiar and aware, the tributary area for this beam would be defined as all the area halfway over to the next floor beam and halfway over to the next floor beam. So would you agree that the tributary area would probably look something kind of like this? This would be the tributary area. This would be how much that floor beam is responsible for. Anything past that on the left or right, so anything over on the right side, this beam's going to take over. Anything on the left side, this beam's going to take over. And anything above, let's say, anything above this, well, this beam's going to take over. Does that make sense? So you're just divvying up the floor into how much a given element is responsible for. Make sense? Okay. Now, just so everybody's clear, okay, so how long is this floor beam? 30 feet, okay. All right, yes? Well, that's okay. So if you're standing in the middle, so half goes here and half goes there. You see what I mean? And one thing to keep in mind, I mean, yeah, you are thinking of this, you know, if you're talking about an individual person, but keep in mind when we look at live loads on floor systems, we're not really looking at individual people. We're looking at this as if we have sort of an average pressure load. So we got, what, 30-some people in this room. What we would do is we would idealize this as something like 50 pounds per square foot. Even though there's different people, you know, split up it's going to be split up to different beams. On average, this 50 pounds per square foot, if you will, you know, half of it's going to go here and half of it's going to go there. Does that make sense? Again, I see the temptation to treat individual people like, well, where does an individual person go? But we're not really treating it like that. Now, let me also say this. If you have a large piece of equipment, you know, like equipment for the elevator or for the HVAC system or something like that, then that would be a little bit of a different story, but you're going to treat that individually anyways. You know, you're going to have a large, let's say, concentrated load on a given girder, and you're going to analyze that element separately. Does that make sense?
Different story. Talking about elevators.
That was, I didn't even notice that. That was pretty good. Different story, different elevators. That was pretty good. Okay. Everybody okay with this? All right, let me try and draw this out and kind of explain what's going on. Okay, first off, before we get into this, now the length of this beam is 30 feet. Now, what is the tributary width? Let me ask you this: how wide is this? Let me scroll down so y'all have the dimensions. Like, how wide is it from, you know, here to here? It's 10, right? Because that's 5 and that's 5, so this is 10. Okay, just want to make sure everybody's clear on that. All right. Okay, so everybody can read that, right? Okay. Okay, so just so everybody's clear, okay, so the length of the beam is 30 feet. Here, let me move that out of the way. That's going to bug me. 30 feet. and we'll call the tributary width 10 feet. Everybody okay with that? So while we are not going to directly use this right now, just so everybody's clear on this, what would the tributary area be? 300 square feet. We're not going to use that right now, but we will sort of use that later on when we look at reduction. But we'll get to that here in a little bit. Okay. Sound good? Now remember, we've got floor beams that are spaced every 10 feet. So if I were to look at this floor system, it might look something kind of like this. It might, I'm going to do my best to, get my artistic, representations accurate. I can do a little better than that. Okay, no, I can't. We'll just leave it at that. You know what? This is going to bug me. I'm doing this again. There's a point I'm getting at with this. So I sort of need 3. Okay, I like that one better. Well, you can deal with it. Okay, all right. So let's say I've got floor beams and they're sort of going on, forever. So, there's, even though there's only like 5, we'll just say, they're sort of going on ad infinitum. Okay? Now, again, we're treating our load as if we have sort of a uniform pressure load on this floor system. So imagine that you have sort of a pressure load that looks like this. And keep in mind, okay, this is 3D, okay? The floor system sort of goes like this, okay? So you have a floor load, or pressure load that's being applied over this entire floor system. So it's something like that. Sound good? Okay. Now just so everybody's clear on the dimensions, so again, this pressure load is 20 pounds per square foot, and we've got floor beams that are spaced at, what did we say, 10 feet?
Yeah.
There we go. 10 feet and 10 feet, okay? So if we're investigating, let's say, a representative floor beam, let's say we're looking at this one in the middle, it is responsible for all the load halfway over to the next one and halfway over to the next one. So its tributary area might look something like that. So sort of that blue slice, or that hatched slice that you see right here, that's what this floor beam is responsible for. Sound good? Okay. And so this dimension is 10 feet. Let's see, this is testing out my 3-dimensional art abilities, my perspective. That's not bad. That's about the best you're going to get out of me. Thank you. Thank you. Okay. Now, what we're going to do is this, okay? Now, when we analyze a beam in structural analysis, I mean, we analyzed it as if it was a line, just a single line, hinge, roller, etc. So what I'm going to do is this. I'm going to take that pressure load, bless you, I'm going to take that pressure load and I'm going to idealize it as if it was a uniformly distributed load along a single beam. So in other words, I'm going to try and take this and I'm going to turn it into this. I'm going to say, well, what if we were just looking at that beam, and instead of this pressure load, let's look at it as if it was just a single uniformly distributed load. And it's a little, easier than you might think. It's pretty simple. Let's just use some common sense. If I have 20 pounds per square foot over a floor system, and one beam is responsible for 10 feet of that, so 20 pounds per square foot over a width of 10 feet means that beam is experiencing how much? Think about it. If I have 20 pounds per square foot, and I'm responsible for 10 feet of that, then I'm seeing, what, 200 pounds per foot? Make sense? Everybody okay with that? So I propose that if I was looking at this as if it was a uniformly distributed load, this would be 200 pounds per foot. Make sense? If that's complicated, think about it like this. The tributary area is what, 300 square feet? So there's 20 pounds per square foot being applied over the floor, and this beam is responsible for 300 square foot of it. So what's 20 times 300? Is that 6,000? So one beam is seeing 6,000 pounds, but that beam is, what, 30 foot long? So every foot, how much is it seeing? Seeing 200 pounds. Make sense? So from a structural analysis standpoint, I propose that here's our model. So this is 200 pounds per foot. We'll say this is a hinge. We'll say this is a roller. Now, it really doesn't matter which one's the hinge and which one's the roller because there's no loads going left or right. You know, there's just a vertical load, so it really doesn't matter. And this dimension is what? How long is the beam? 30 feet. Make sense? Now that's a beam I can analyze. That's a beam I can design. So what we're doing is we're taking this three-dimensional floor system being subjected to a representative load and turning it into something that we can analyze and we can ultimately design. Does that make sense?
So why one a roller and one
It doesn't matter. I mean, you could switch it. What I'm getting at is this. First off, just from a structural analysis standpoint, I mean, we would put a hinge on one of them and a roller on another one. It's not going to matter which one because there's no loads going left or right. There's just vertical loads. So think about it like this. What are the reactions going to be? Does anybody calculate what the reactions are going to be? 3,000 pounds, right? Because there's, you know, what do we have? 200 pounds per foot times 30 foot divided by 2, right? So the reactions are going to be 3,000 pounds. So we'll say, you know, the reactions, I'll call it the reactions for the beams, is going to be 1/2 200 pounds per foot times 30 feet, which is 3,000 pounds, or 3 kips. Sound good? Now, let's say you can't remember. Let's say, oh man, I can't remember this. Anybody remember this? I gave you this on Monday. This is the first handout that I gave you for this class. What this is, this actually comes out of the timber specification, but I think it's the easiest to use guide like this that there are. What this is a collection of basically simplified representative analysis problems and all the results. If you go to the very first one, which is on page 4, I think, of the handout, look right here. Simply supported beam, uniformly distributed load. Here's your reaction, WL/2. So if you have, 200 pounds per foot, 30 foot, plug and chug. What's the shear diagram look like? What do? You go up, down, so down, lot to a little to a lot. Y'all remember that? Bam, there's your formulas. I know you're sitting here going, now, why didn't you give that to us last semester? Like, really? You show us this now? Well, the point was so that you would understand this when you got it. So you got to, walk before you can run, right? Yeah. So what this, let me say this, okay? Because I know, some of you are going to ask, well, are we going to get any crazy, complicated structural analysis problems in this class? The answer is Not likely, okay? This is not structural analysis, this is reinforced concrete design. Everybody in this room already proved to me that they can perform structural analysis because they passed the class, okay? That doesn't mean that you don't need to understand some basics, okay? And I also want to emphasize that if you don't understand how to use these guides, don't use them. Break out the structural analysis that I taught you last semester. But these guides can save you a little bit of time. In other words, like if you have a simply supported beam with a uniformly distributed load and you need to know the maximum bending moment, you can do the reactions, draw the shear diagram, draw the moment diagram, because I know everybody here can do it, or you can say WL squared over 8 because it's right there, okay? So you can use it or not. I just wanted to make them available to you. Sound good? Any questions? Okay. Now, so I'm not going to continue this analysis portion any further because you've got this. And from here, if you all can't draw the shear diagram or the moment diagram, well, then I failed as a professor last semester. I know you all can do this. So, all right. Now, oh, wrong one. Now, let's go back to the example. Okay, so we've handled a floor beam. Now let's look at a typical girder. Let's look at C2D2. Okay, so C2D2, we're looking at this right here. Okay, so here's our floor. Yes.
So, what you just said covered like the first bullet point.
Yeah, basically.
Does it matter like how would we locate which one we did and which one?
It won't matter because that's a good question. So you're saying like which one that you did? Let me ask you this: is this one gonna be any different than that? They're all the same, yeah. Now for girders and for columns, that's where the C2D2 or the column A1 comes into play because that's where the grid reference comes into play. For a typical interior beam, it's not going to matter. Now let me follow up with that. Let me ask you this: what's the difference between a typical interior floor beam and a typical exterior floor beam? I'm curious. What? Exactly. These floor beams, and by exterior floor beams, I mean the one along the lines either D or A. The difference between these floor beams is that the tributary width is only 5 feet instead of 10 feet. Make sense? So theoretically, these floor beams would be a little smaller. They're not as responsible for as much. Okay? Now, that is only if they are subjected to floor loads. That might not be the case. What goes all the way around the outside of buildings? The wall, the facade, either brick or precast. And if those are mounted on, let's say, the exterior beams, then they're going to be subjected to a lot of load, not just the floor load inside the given floor, but they're also going to be subjected to that load around the wall. So you wouldn't really consider it into the area. What you'd probably do is figure out how much the wall weighs per foot and then say, well, the wall, so much per foot times however long it is. Does that make sense? It also depends on how it's mounted. Like if you have a mounting bracket right in the middle, then just say, well, the wall weighs 70 pounds per foot, 30 foot, just a point load right in the middle. It just depends on how it's mounted. So that's a good question now. Sound good? All right. Okay, so yeah, for if it's a typical interior floor beam, you really wouldn't need to indicate because they're all the same. Let's look at our girder. Okay, let's look at C2D2. So we're talking about this girder right here. So first off, the tributary area would be, we're talking about girders, so halfway over to this girder, halfway over to that girder. So we're probably talking about something kind of like this. Does that make sense? So right off the bat, do you think girders, and the term beams and girders gets used a little interchangeably in structural engineering, but I like to think that beams frame into girders. That's sort of how I think about it. Which do you think are going to be bigger, beams or girders? Girders, right? Girders are subjected to more load. Okay. Now, there's also a little bit of engineering judgment that needs to go into girder analysis. one way to analyze a girder is literally just treat it as if it's a beam. So the exact same way we did this. So what would be the tributary width of this girder? The tributary width. 30, right? That's 30, and then the beam is 50 foot long. So literally do what we just did, just make the tributary width 30 and the length 50, and just do that. That's one way of handling a girder analysis. I don't think that is as appropriate for a frame like this, and I'll get into why here in a second. What I would like to do is instead treat this as if it's a hip bone, leg bone analogy. In other words, I've got a girder that's 50 foot long, and instead of treating this as if it's got a big distributed load on it, how many beams are framing in? I got 4 beams framing in, right? Think what's happening here, okay? Let me go back to this. Here's my beam, right? And we said that what? This has a support reaction of 3 kips, and this has a support reaction of 3 kips. I mean, where is that beam framing into? Is that connected to the ground? No, it's connected to the girder. So why don't I do this? Why don't I instead of treating my girder as if it's another beam, why don't I do this? So girder C2, D2. Why don't I do this? Why don't I say I've got an element that's how long? How long is the girder? 50 feet. But instead, I've got 4 point loads framing into it. We'll do that. So this is 10 feet, 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 and that makes this 50 foot long. Now, how much are each of those point loads? Somebody's saying 3 kips. Are they 3 kips? They're 6 kips, right? Why are they 6 kips? Because there's 1 on each side, right? So here's the floor system. You know, I've got this floor beam. It's carrying 3 kips over, but I got this floor beam that's carrying 3 kips over. So I got 6 kips here, 6 kips here, 6 kips here, 6 kips here. What if I was doing this one, C1D1? It'd just be 3, right? Make sense? Because, all right, here's a floor beam, right? This floor beam has 3 kips here and 3 kips there, right? But so does this one.
Okay, so you're taking the 3 kips from what we got before.
Yeah. Okay. This floor beam had a reaction of 3 kips, right, on each end. But that's the same for all the floor beams in the system. What I'm saying is, right here at this point, how many floor beams frame in here? 2, right? Think, this is a floor beam and it's got support reactions. Those support reactions are going right there. So I've got 3 kips from this side, 3 kips from this side. Does that make sense?
So that beam is 3 kips per foot.
No.
The beam, not the girder.
No. All right. Let me do this, okay? So let's take a look at that floor beam, right? That floor beam is just like this one down here. It's a floor beam. It's got 200 pounds per foot, and the support reaction is 3 kips. 3 kips, right? That's the same thing as this one right here, right? Make sense? What I'm getting at, I mean, see the support? That's not the ground, okay? That floor beam is framing into this girder. You see what I mean?
So this supports the girder.
Yes. Think. Go back to this. Oh, goodness. I don't know what happened there. What's that? Think about this. Here's the beam, right? The support is not the ground. The support's the girder. That 3 kips is going right here. No. But keep in mind, the difference between what you're seeing in this image and what we're looking at with this beam is that there's another beam on the other side of it. So there's 3 kips here and then 3 kips there. Does everybody else see that? Everybody okay with that? Okay. So I propose, now I'm going to have to, I'll redo that here in a second. I propose that if here's my analysis model, this is 6 kips. This is 6 kips. This is 6 kips. Exactly. Yeah. Does this all make sense?
That's where the beams are going in.
Yes, exactly. Yeah. So that would, so what would that make the reactions then in this case? 12, right? This is 12 kips. This is 12 kips. Is this making sense? Is everybody okay with this? Hip bone connected to the leg bone, right? Now, what's my shear diagram going to look like? I'm just curious. It's going to go up 12. Then it's going to kind of look like a stair step, right? It's going to go boop, 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 right? Make sense? Yes. Yeah, and I'm going to get to that here in a second. Just bear with me. Okay. Any questions so far? Okay. Now Mr. Masters is asking, what if you treat it as if it's a distributed load? Okay. You will get slightly different answers. Okay. The question though is, when do you do one versus the other? Okay. Here's my answer. Okay. And this is a rule of thumb. This is where engineering judgment comes into play, but statics would dictate that you always do this. Hip bone connected to the leg bone. You always frame support reactions into the girders. Girders go to the column go to the ground. Okay. Now, we have, if we're looking at a given girder, we have what? 1, 2, 3, 4 floor beams framing into it, right? What if we had 40 floor beams framing into it? Just bear with me, okay? You would agree that the shear diagram for this structure right here looks like this. We'd go up, we'd go over, go down, go over, go down, go over, go down, go over, go down, go over, go up, right? That's with 4 floor beams, right? Let's say we had 40. If you had 40, it'd be like, right? That's essentially what it would look like. Well, if it's that many, why not just treat it as a distributed load and just do that? You see what I mean? Okay, so you want my rule of thumb? If you have more than 4 floor beams, just do the distributed load. If you have less than 4 or less, do this. Does that make sense? You will get some slightly different answers, but it's so minor that it doesn't really matter. I would do it the area way if you had like 5 or 6 or 7 floor beams. Exactly like you did this. The only difference is the tributary width would be 30 feet and the length would be 50 feet. Exact same thing. Literally just changing numbers. Does that make sense? Everybody else okay with this? If you got, please, you got any questions, this is time.
We're also looking at the beams that are going directly to the columns and just kind of disregarding them. They don't go to a girder.
Yeah, we're getting to that here in a second. I'm glad you brought that up. So the beams that are going into the columns, that's coming up here in a quick second. Yes? No, well, hold on. Let me see. What is the number? Let me see. So it's, let's do the math. So here's the, let me do this. Here's the girder. So this is, that's our tributary area. The width is what, 30? And what was the load? 20 pounds per square foot? So 20 times 30, yeah, it's 6,000. Did I do that right? 600 pounds per foot. Does that make sense? So 600 pounds per foot over a beam that's 50 foot long. Does that make sense? Literally just changing the numbers. So. Everybody good? Now, there is an added benefit to breaking them up into point loads, and that's when you look at the columns. Let's look at the columns. Okay? Let's look at the columns. So what column are we looking at now? B2? So what is the tributary area for B2? I would say it looks something about like this. Is that about right? Everybody okay with that? What are the dimensions? What did you say they were? 50 by 30, right? Because if I look on the x-axis, that's 25 and that's 25, so that's 50. On the y-axis, that's 15 and that's 15, so it's 30, right? Sound good? Now, the benefit of treating them like, support reactions, hip bone connected to the leg bone, is what happens with the column. Like, check this out. Okay? All right, so let's look at the column. Okay, so watch this. So method 1. What did we say that the tributary area would be? It'd be 50 foot times 30 foot. What is that? 1,500 square foot, right? Now, what's the pressure load? So would you agree that the load on that column is 20 pounds per square foot times 1,500 foot squared, which is what? 30,000 pounds or 30 kips. Would you agree with that? Okay. Now, Mr. Filsinger had a question earlier. He said, well, what about the columns? There's beams and girders framing into it. Watch this. Remind me, what was the reaction that we calculated for a beam? 3 kips. And what was the reaction that we calculated for a girder? 12 kips. Okay? Let me ask you something. Here's our floor system. If I look at column B2, how many girders frame into B2? 2. This one and that one. How many beams frame into B2? This one and this one. So why don't I do this? If I could say that the load on that column is going to be 2 beam reactions plus 2 girder reactions, which is 2 times 3 kips plus 2 times 12 kips. And what does that come out to be? What do you think?
We learned enough today to take Friday off.
I didn't say that.
Good job.
But yeah, good effort. Good effort, good effort. What do you think? Now think about this though. 20 pounds per square foot. I mean, that's not a lot of load, but think just from one floor, we're getting 30 kips on just a single column. Another thing to keep in mind, this is looking at this building as if it was a 1-story building. We're only looking at 1 story. Imagine if this was a 10-story building. We'd have 300 kips on the ground, right? We'd have a column, and then as the column went down, it got heavier and heavier and heavier and heavier. Does that make sense? What do you mean start at the top?
So you're analyzing a 10-story building, would you start at the top? Because there's nothing above it that you have to worry about.
Well, there's snow.
I mean, just your normal, that's your normal PSF load. You're accounting for the snow on top of the road and then going down from there.
Let me analyze it. Let me answer it like this. Okay? Let's do this. Okay. If you had, let's say you had a multi-story building. Let's say you're looking at a given column. in that building, and you've got floors framing into it, etc. And let's say that's the ground. Okay? Sound good? Let's say that every story adds another 30 kips, right? So that means that this section of the column would be experiencing 30 kips in compression, right? This part would be experiencing 60 kips in compression. This part would be experiencing 90 kips in compression. This part would be experiencing 120 kips in compression. Make sense? So what I would say is that the column could get a little bigger or get more heavily reinforced as you go down.
But you wouldn't have to change the beams or girders per se.
No, that's a great no. The question was, do you have to change the beams or the girders? The answer is no. Like the floor beam on the second story of a building doesn't behave any differently than the floor beam on the 82nd story of a building. I mean, it doesn't matter. Floor beams don't really care where they are because all they're seeing is, the load of itself weight and people and stuff like that.
But as we gain elevation, we look at a higher wind.
You're exactly right. But that's a different story. Yes. Shear wall or moment frame or something like that. Yes. This is stuff we're going to be talking about. Y'all are getting ahead of me.
Just want to graduate now.
What do you think? Any other big questions? You like this? Yeah. Now, you senior design folks are going to get a lot of experience with this here in a little bit. So, all right. Well, I guess you all will too if I'm teaching it next year. So, I'm just trying to get to like 1050. So, all right. Okay. Are there any other questions? Any other questions? All right. Yes.
So are we ultimately doing all these calculations to be able to say how big our columns are?
Yes. Yes. That's what design means, to size the individual elements so that they can safely resist those loads. You got to know what the loads are in order to do that. So, yeah, that is the ultimate end goal. Okay. Let me talk a little bit about loads because we kind of need to get into this a little bit. We'll continue this on Friday, and then you'll be well prepared to assess your homework. But let's talk about loads. Okay, there are really 5 main load components that structures see. 3 of them act in the direction of gravity, which is what I'm mainly concerned with, that you have the ability to assess, and 2 of them act laterally. So the 3 that act primarily, in a gravity effect are dead loads, live loads, and snow loads. The 2 lateral effects that we deal with, another lateral meaning side to side, is wind and seismic events like earthquakes. But where do you get them from? Where do the loads come from? Like I said that a library is around 150 pounds per square foot. A classroom can be like 40 to 50, something like that. Did I just make that up? Where did that come from? Well, they come from specifications. Now, they come from published standards within our engineering community. Now, I know everybody in this room has heard of ASCE, but up until now, ASCE has probably been little more than a social organization where you build a concrete bowling ball or a canoe or a bridge every now and then. And that's true. I mean, ASCE provides that function, but they are much more than that. One of the main roles that ASCE plays in the engineering community is they are the ones that provide a lot of the technical standards that we use as engineers. And that they will produce standards on how to design dams and how to design roads and so on and so forth. One of the most commonly used standards is ASCE 7. ASCE 7 is the standard that delineates minimum design loads on buildings and structures. I have here ASCE 710 because that came out in 2010. We actually recently updated to ASCE 716, which came out in 2016, but there's not a lot really changed between ASCE 710 and 16 that would really affect us, bless you. And a lot of the gravity load provisions haven't changed for years. The maps might have changed, but I've got an online tool that'll help you with that. Let's take a moment and talk a little bit about some of these loads. I want to start off with dead loads. Okay. Now, whenever I use the term dead load, really what I'm talking about are loads that are stationary, loads that don't move. I am obviously not a dead load because I'm walking right now. I'm walking across the room. But dead loads are loads that are stationary. We're talking about the structure's own self-weight. We're talking about any permanent attachment, anything that's not going anywhere. And by and large, I'd say 90% of all dead loads that we consider as structural engineering are self-weight, the structure's own self-weight. Now, the most common civil engineering materials that we use are steel and concrete, okay? Now, just so everybody is aware, the unit weight of steel is 490 pounds per cubic foot. That's a number that you'll want to drill into the back of your head. Not so much of importance for this class. The one that's important for this class is the unit weight of reinforced concrete. Now, the unit weight of reinforced concrete is variable. It changes. I mean, you all know that for those of you that had civil engineering materials last semester. I mean, everybody did the analysis of everybody else's data, and you all calculated unit weights, and they were all over the place, but not crazily all over the place. I mean, they did have a little bit of a range. One of the things that should be noted is like what we did last semester with the unit weight of concrete. What did those cylinders not have inside them? Rebar. They didn't have any rebar, any reinforcement. So reinforced concrete is a little heavier than regular concrete, okay? What we typically assume in civil engineering is we typically assume that unreinforced concrete weighs around 145 pounds per cubic foot, and what we typically do is to account for the reinforcement, we add a little bit. So the 150 pounds per cubic foot, that accounts for a little bit of a bump in weight for the fact that there's steel in there, because the steel is heavier. So unless otherwise stated, we are going to use 150 pounds per cubic foot for unit weight for everything that we do. And we will reference that number quite a bit in here, so it's something you'll want to probably just have burned into the back of your head. Now, if there's any other weights or values that you need, there's really two big places that you can get them. One is ASCE 7. So if you open up ASCE 7, there's hosts of different floor loads, like for instance, common floor dead loads. Are you looking at ceramic tile? Are you looking at gypsum fill? Or you have normal weight concrete flooring? Do you have metal deck? For each of those flooring loads, depending upon what you're looking at, you have a different, like quarter-inch ceramic tile weighs around 10 pounds per square foot, or that's the upper bound value you should use for design. If it's not in ASCE 7, the next place would be is call the manufacturer. If you're using some floor system or some deck pan, either call the manufacturer, look it up in their catalog. They'll have those weights listed, so just use those. So those are really the two big places that you would get those loads. The third would be to just compute it. Now, one thing, this is probably where I'm going to close it, because this is really kind of an important aspect. When we look at beams, the most common load that we will consider, or the common loading scenario that we will consider in this course, is a simply supported beam with a uniformly distributed load. The reason why is because what load must all beams be able to withstand? Their own self-weight, okay? Let's look at this beam, okay? Let's say it's a rectangular beam. It's B wide, H tall, and it's L long. So the volume of this beam would be length times width times height, right? Sound good? Now, let's say that this beam weighs 150 pounds per cubic foot. If I have 150 pounds per cubic foot and I multiply it by the volume, the cubic feet, that would tell me the total weight of the beam, right? But that's the total weight of the beam. That total weight is not just lumped right in the center. It's distributed over the length, right? So if I take that total weight and say the beam is 20 foot long and the beam weighs 6,000 pounds, well, its weight per foot is 6,000 divided by however long it is, right? Sound good? So a shortcut way to determine how heavy a beam is per foot is to take the unit weight and multiply it by the area, B times H. Because what you're doing is you're ultimately multiplying it by the volume, but then you're saying that per foot. So BHL divided by L, you're just canceling out the L's. So in general, if you take the unit weight of a material and multiply it by the area of that beam, that will tell you how heavy the beam is per foot. Does that make sense? Everybody okay with that? Any questions? That's where I'm stopping. We'll pick this up on Friday. That's all I got. Oh, one more thing before I end. If you are on the old curriculum, I'm going to get the sign-in sheet here a second. Come tell me so that I know, because I need to know that. So, all right.